Hello, and welcome to this Appfarm Developer Forum webinar. In this webinar, we're going to be discussing data modeling in Appfarm Create. In part 1, we'll take a theoretical approach. We'll discuss data modeling and normalization, and theories and best practices relating to this. And then in part 2, we'll take a more practical approach. We'll do a live session where we're given a list of tasks, and we'll build a data model together, which solves these tasks. So, let's begin. Let's begin with part 1. Part 1, as mentioned, is a more theoretical approach to data modeling and concepts and best practices, both relating to data modeling and normalization. We'll start by discussing the different relationships that objects can have. The first possible relationship is a one-to-one relationship. This relationship type is where one object is connected exclusively with one other object, and vice versa. For instance, in the diagram on the right, we can see that one person object is connected to one settings object, and vice versa. This relationship can be combined with uniqueness constraints to enforce data integrity. However, this relationship type is rarely used in practice. The next relationship type is one-to-many. One-to-many relationships are the most common relationship types that you will find in databases. A one-to-many relationship is where one record in one table can be associated with many records in another table. However, the records in the second table can only relate to one instance in the first table. A common use case where this is put into practice is using orders and order lines. Each order can have multiple order lines, but each order line can only be associated with one order. In Create, this is modeled by having a reference to the order object on each order line, which points towards a specific order ID. This order ID acts as the primary key in the order table, but acts as a foreign key in the order lines table. This relationship type is often useful for cascading functionality, for instance, deleting, where if you delete an order, you can delete every order line which is associated with that order using the cascade delete functionality in Appfarm Create. The final relationship type we're going to discuss now is many-to-many relationships. Many-to-many relationships are instances where many objects can be associated with many objects. A single book, for instance, can be written by several authors, and one author can have written several books. So the many relation goes both ways. To model this in Appfarm Create, we use a join class, which uses the primary key from the author table and the primary key from the book table as foreign keys in a join class, in this instance called written by. Each row in the join table represents a specific combination of book and author, where each author and each book can appear multiple times in different rows. This method allows more metadata to be stored about the relation between author and book, if required as well, by adding a new property to the join table. This is another very common relationship type, and is very scalable as the number of books. So now that we've discussed relationship types, we come to data normalization. Normalization is the process of restructuring a relational database in order to adhere to rules and guidelines, which make up so-called normal forms. This process helps to reduce data redundancy and simultaneously improve data integrity. The theoretical normal forms range from unnormalized up to sixth normal form. But in practice, you only really see data models up to third normal form. The process of normalization is demonstrated in the diagram on the right-hand side, where we begin with one big table, which is unnormalized. And then we begin to make changes and split the data up into several tables to begin to adhere to first normal form, second normal form, and third normal form. But the best way to demonstrate normalization is through an example. Here we have a potential dataset for a local library clerk. The dataset is used to track customers and which books they have loaned out. It is safe to say that this dataset is unnormalized. It may work to a certain extent for a very small user group, but the scalability is not very good at all. What if an author changes their name, for instance? then each specific order where the author is referenced will need to be changed manually each time this happens. There's several values in some cells, several books in one order, or several authors, or several genres. We also have no way of identifying each specific order. Without any order ID or identification, it is difficult to refer to a specific order. You can also see that there is redundant customer information, which is listed in the order table, which we can fix as well. So the first step is to take this dataset from unnormalized into first normal form, also called 1NF. First normal form has 3 criteria, which is listed on the left here. Each record has to be unique, with no duplicated rows or columns. Each cell needs to contain a single value, so there's no instances of multi-reference values, which was what we discussed earlier about some cells having multiple books or authors. There should also be consistent data types. All values within the same column need to be the same data type. You can see in the dataset as it exists now, we already adhere to the third rule, as each column has the same data type in every row. However, there are improvements to make before we can call this dataset normalized to the first normal form. Here is a potential example for this dataset where we've gone from unnormalized data to the first normal form. You can see instances where there were multiple books or multiple authors or genres in one cell have been split into multiple lines, and each line has its own order ID, which is unique. With these fixes, we've now achieved first normal form. But as you can probably see, there's a lot of repeated data. So this should be fixed. So let's look into how this can be done. To go from first normal form to second normal form, there's actually only 2 rules. And the first rule is that it's already on first normal form. So the rules from first normal form still apply. And then the other rule is that all non-key attributes are fully functionally dependent on the primary key. This is a complicated way of phrasing it, but in practice, this means that every single column in this table should depend in some way on the order ID. For instance, we can see that the due date of the order is dependent on the order ID, but the customer's phone number has no functional dependency on the order ID at all. So we can keep the due date of the order in the orders table, but any customer metadata, which is not functionally dependent on the order ID, needs to belong in another table, where it becomes functionally dependent on a customer ID. So in this case, we have the customer's phone number and the customer's email address, which should be functionally dependent on a customer ID, rather than the primary key of the order table. We have author information and genre information, which is not dependent on the order ID, but more on a book ID. So we should split this dataset up into multiple tables. So we can begin by creating a customer table. Each row now has its own unique customer ID, and each row represents a different customer. We have split the full name into first name and last name values. We can see now that in this case, all of these 4 columns are functionally dependent on the unique customer ID. Now that we have unique customer identifiers, we can go back to the order table. Step 2 is to replace all of these customer fields with a unique customer ID, which refers to the unique customer ID in the customer table. This now acts as a foreign key in the order table to link to the customer who has placed this order. The customer name, phone number, and email address columns can now be removed from the order table, as they are not functionally dependent on the order ID, but they are functionally dependent on the customer ID. The due date, as discussed, can remain on the order table, as it is functionally dependent on the unique order ID. And now in step 3, we can create a new book table. Each book has its own ID now, with a title and an author property. We can remove these properties from the order table and instead refer to the unique book ID, which acts as another foreign key in the order table. We've now replaced customer information and book information in the order table with these 2 foreign keys. Some may notice that we have a column in the book table which still needs to be fixed. The author name is not functionally dependent on the ID of the book, but it would be functionally dependent on the ID of the author. So let's create an author table, which we do in step 4. We now have an author table, where each author has a first name and last name and a unique identifier, which now acts as a foreign key in the book table. You may notice, however, that we've pushed ourselves into a bit of a corner with this relation. One book can only have one author. So, as discussed earlier, let's fix this by a join table to create a many-to-many relationship type, where now we have book ID and author ID acting as foreign keys in the written by dataset. Each row in this join table represents a specific combination of book and author. And now in step 5, we can do what we've done already for books and authors. We can now fix this for books and genres. As each book can have many genres, and each genre can belong to many books, we need to create another join table, which links genres and books. So we've done this here. Each genre has been given its own ID with the genre name, and we've created a join table where the book ID and the genre ID act as foreign keys together in the book genre join table. With this fix for book genres, we now have a dataset that theoretically meets the criteria for second normal form. But you may notice, like we discussed earlier, the orders are actually missing order lines. Orders need to have multiple order lines to account for multiple copies of the same book being given in the same order. The omission of order lines in this case was deliberate, to show the difference between a dataset which theoretically matches a normal form and a dataset which actually solves the problem at hand. Now that we've discussed second normal form, let's go and discuss third normal form. The previous dataset which we worked with normalizing was already on third normal form, so we've got a new example on the right-hand side of a new table. For a data model to meet third normal form, there are again 2 criteria. It needs to already meet second normal form, and therefore first normal form. The second rule is that there can be no transitive dependencies for any non-prime attributes. Again, this wording is a little bit complicated, but in practice this means that there cannot be any dependencies in one table where it depends on a different field, which is not the primary key. For example, on the right-hand side, we can see that department name is dependent on department ID, and department ID is dependent on the primary key. This is a transitive dependency, and it's a dependency on a field which is not the primary key in this table. In practice, if we wanted to change the name of a department, we would now have to change the name in every single employee which references this department. So to meet third normal form, let's create a new department table, where we have the department ID and the department name, which is functionally dependent on the department ID. And now it acts as a foreign key in the employees table to the department ID. We can simply remove the department name column to remove this transitive dependency. And we now instead have this relationship between employees and departments without needing to list the department name in every single employee row. With this fix, our data model is now in third normal form. There are other normal forms which go beyond third normal form, as previously mentioned. However, these are very rarely seen in practice. These are only really theoretical. When you're building real data models, other factors such as performance and convenience for the developer come into play, which means that most real-life data models are rarely above third. So now we've discussed a lot of theory for normalization. But let's discuss now how it actually works in the context of Appfarm Create. Appfarm Create actually uses MongoDB, which is a document database and not a relational database. Data in the database is saved in JSON format and not the rows and columns which we've been discussing previously. Document databases are not made for normalization. What Appfarm Create does have is a built-in layer between the database and the user, which allows for relational referencing. This layer builds upon the document database to give the impression of relational data modeling, so we can use the theories and best practices which we've discussed already in Appfarm Create. The document database structure seen on the right can be translated into something you're more familiar with using this built-in layer. You can see this representation on the right-hand side now. It forms a join table, as we've discussed already, between author and book. In most real-life scenarios, you want to aim for a data model which satisfies at least second normal form, but you don't necessarily want third normal form. There are cases where we want to denormalize, as discussed previously, which allows for better performance or better convenience for the developer. The goal for normalization should not be the highest degree of normalization possible. Normalization should simply be used as theories and best practices to allow for improved data integrity and reduced data redundancy. But there is a balance between these and actually solving the problem at hand in a convenient way, both for the end user and for the developer. There are many real-life use cases where denormalizing actually makes sense. For instance, to add a new property to avoid deep data bindings, which improves the convenience of read operations. In a real-life example, if we had a project table, a project company table, and a project employee table, in practice, the only way to access the project from project employee would be to go 2 layers deep in the data model. If we had a fully normalized data model in third normal form, this would be the case. We would have to go through company to get to project. This can be solved in the context of Appfarm Create by adding a project relation to the project employee data source. While this breaches third normal form, this makes read operations a lot easier as we have a direct link to the project without needing to go through the project company. Some of you may know that Appfarm now has multi-references. Multi-references go against every principle of normalization we've discussed, as these are a breach of first normal form, where each cell needs to have one atomic reference. Multi-references allow the user to save several values in the same cell by introducing a list of elements. For instance, this relationship between book and author, which has been discussed a lot today, can now be represented using multi-references, where a book has multiple references to authors. In the cases where multiple authors have contributed on the same book, this is now represented as an array in a single cell. Each element in this array is a foreign key, which references a specific instance in the author table. Multi-references might be a breach of first normal form, but in practice, not every data model has to reach third normal form to be suitably robust for a specific use case. Appfarm Create being built upon a document database with this additional layer for relational modeling gives the best of both worlds. You can normalize using theory and best practices, but you can also build a data model which works for specific use cases. While multi-references are a breach of first normal form, as we've said already, there are use cases where this is useful. This example on the right-hand side is only relevant where to represent the relationship between book and author, we only need the author ID. If we needed more metadata about this relationship, then the join table, which we've discussed already, would come into play again. For instance, if we wanted to track the number of pages which each author wrote for each book, we couldn't do this with multi-references, so we would then need to create this join table, as we've discussed already, and create the many-to-many relationship in this way. This brings us to the end of part 1. Part 1 has been very theoretical, so in part 2, we'll take a more practical approach and build a data model in Appfarm Create. So now that we've discussed the theory behind data modeling and normalization, now we're going to take a practical approach in part 2. We're going to be given a list of tasks, and we're going to build a data model that solves this list of tasks. Here we have an empty data model in Appfarm Create, and here is where we're going to build our data model. And here we have our list of tasks. So the first task is already given. We want to save customers with name and email. Each customer has a unique customer number. We should also track who creates or updates a customer. We can first create a customer object class. Give it a tag. And now we have a customer object class. As you can see, the object class is currently empty, so let's add a property for first name and last name. First name type string last name string. Let's make both of these required. Since each customer should have a unique customer number, we can turn on sequential identifier. And this will give an ID which goes up sequentially. And we can start with 100,000 to give the impression that we have many more customers than we actually do. This will mean the first customer will be given an ID of 100,000, and then 100,001, 100,002, and so on. And this will act as the customer number. Sequential identifier can also be useful for other object classes, such as an order number or a project number. We have a first name and last name for our customer, so let's add a function which calculates their full name. Let's add fx to the end so that it's obvious from the data model that it is a function property. We can set the property type to function. Then we can use template strings to build the string and return it using the customer's first name and last name. And then we can add the data source. Now on the object class, we can set the display property to be full name. Let's add a new property for the customer's email address of type string. This should also be required and unique. You can also add a regular expression here which validates the format of the email address, that it is a valid email address given. But we're not going to do that here. Now let's add this new field. Now that we have our object class, let's give the right permissions. You can see that owners, maintainers, and developers get full access to all object classes by default, but any custom roles don't. So let's give app user permissions to create, read, update, and delete a customer. And since the customer object class holds personal information, you can classify it here under which GDPR classification it falls under, and add more GDPR details. You can read more about GDPR in Appfarm Create using the QR code which is on screen now, which goes to the Appfarm documentation. And the last step before completing this task, since the task mentioned that they want to track who created and updated the customer, we can do this by turning on created by and updated by, which are then automatically logged in Appfarm Create. These will be bound to the user of the current user who is logged in when the object is created or when the object is updated. So now we've finished the first task. Let's tick it off. The customer should be able to place an order. An order can consist of multiple books with their independent prices. And we want to be able to track the orders by their states. So let's start by adding a new object class called order. And as mentioned, we can turn on sequential identifier for order with a starting value of 10,000 to give each order a unique order number. Let's add a customer property to our order. Type customer cardinality 1, and let's make it required. And since we want to be able to track each order by state, let's first add an enum, which will be order state. Now, enums have three data types: auto, string, or integer. It is recommended to use integer or string if you expect that this enum will be mapped to external systems, as this makes it much easier to map the values. So in this case, we will use integer. And let's add our 5 values. We can have draft, pending, sent, delivered, cancelled. Let's give each one an ID. 0, 1, 2, 3, and 4. So now we've created our enum, we can link it to the order via a property. Order state, data type order state. Set the cardinality to be 1, and the value on create to be draft. And let's also make it required. Since each order needs to be linked to books, let's first add a new object class called book. For each book, we should track the title, type string, make that required, and the individual prices of these books. The price can be a float. When creating functionality for tracking orders, it is useful to split it between two object classes, your order object class and your order line object class. So let's make a new object class for order line. Each order line should be linked to an order. Only one order. Let's make it required. Let's add the delete rule to be cascade delete. This means that if the order is deleted, all of the order lines linked to this order will also be automatically deleted, which helps remove the cases where there are order lines in your system which aren't linked to any orders. Now each order line needs a link to the book object class, so let's add that next. Cardinality 1 required. We also want the price, so let's add this. Price can be a float, and we'll also make this required. And now we want how many of each book are ordered, so let's add quantity of type integer. We can set the value on create to be 1, and this should also be required. And here we can also set the minimum value to be 1. And finally, let's add an amount property, which is calculated automatically. So let's add fx to the title. This should be of type float. Let's change it to property type function. It should simply return the price multiplied by the quantity, which we can take from the same order line object. So now with our new order line, book, and order object classes, we've solved the second task. So let's check this off. We need to know what the shipping and billing addresses are for each order. This should be saved for the customer to help for speedy checkouts in the future. So here we're going to need to add another object class called address to be able to save it on the customer level and link it to each order. So let's begin by adding our new object class, address. Each address should have address line 1 type string. This should be required. And then address line 2 also of type string, but this shouldn't be required. Now we can add a city property, which is a string, it should be required, and a zip code property, which is a string and should be required. As we discussed earlier in this webinar, tracking city and zip code in this way does not align with the third normal form criteria, but we're choosing to have it denormalized in this case. Each address should also be linked to a customer. Type customer cardinality 1 required. To be able to track which country the address is in, we can add a country object class. So let's add this. Let's give our country a name of type string, which is required. Let's give it ISO2, which is a string, which is required. The maximum length, 2 characters. And let's also give it ISO3, which is also a string, should also be required, but with a maximum length of 3. ISO2 and ISO3 should also be set as unique. These are unique identifiers for each country. Now that we've added our country object class, we can go back to our address object class and link it to the country. Type country required. Now that we've finished our address object class, we can add 2 new properties to our customer. The default shipping address and your default billing address. Both of these should be of type address and required. Type address and required. So now we have addresses which are tracked on the customer level. To end, let's add shipping address and billing address as properties on our order. Type address required and billing address. Type address required. And with that, we've solved this task. So let's check it off and see what the next one is. We need a way for the order to be available for the customer to check for updates, but we can't afford more user packages. Now this means they want to be able to create an app which allows the user to track their order, which also gives unauthorized access to this app, so that the user doesn't need a user object. So let's make some changes to our data model to fit this requirement. Now I'm not going to worry now about creating this unauthorized app, but what we need to do is make some changes to the order object class. We can turn on this random identifier property, which will give each order a random ID instead of a sequential ID. This means that IDs which are exposed in the URL or shown on the screen do not give the user access to be able to guess the next or previous order which another customer has made, which would be very possible with your normal sequential ID. It is also possible to turn this property on for an object class which already has data inside it, and then use GraphQL to go back and give a random identifier to all of these properties which were created without one. There is another QR code on screen which will take you to the Appfarm documentation, which gives the GraphQL query which can achieve this. So now that we've given each order a random identifier, we've solved this task. So let's move on to the next one. We want to avoid multiple employees editing the same order and overwriting someone else's work. Now this, like the last one, only needs one checkbox to be enabled. So let's go to the data model and discuss that now. This change will also need to be done to our order object class, and we can turn on this property here, strict object versioning. Now, as you can see, when we turned on this feature, we got a new property here called version number. When an order is persisted, it is compared with the version number which is stored already in the database. If the version number in the database is higher than the version number stored on this order, that means that updates have been made from somewhere else, and this persist action will fail. This feature is less ideal for object classes which make use of subscribe to updates, or object classes which have many updates which are sent to and from the database. So now we've turned on strict object versioning. We've solved this task. So let's move on to the next one. A book can be written by multiple authors and have multiple genres. We do not need any more metadata. So what we need to do here is to add an author and a genre property to our book object class. So let's add a new object class for our author. Let's give it a first name type string required and a last name type string required. And again, like we did for our customer, let's add a function property which automatically gives the full name of the author. We use template strings for the first name and the last name, which are taken from the author. And once again, on the author, let's add full name as a display property. Now let's go to our book object class and add a new property called authors, which should be linked to the author, but with cardinality many. Since we don't need to store any other metadata about the authors, this is a use for multi-reference on a property. Now, since we want to be able to track the genre of a book, let's create an enum called book genre. Data type string, as we want to avoid using data type odd author. Since we want to be able to track the genre of the book, let's create a new enum called book genre. Give it the data type string, as we want to avoid using data type auto, as we've previously discussed. Let's give it some default values. We can have romance, thriller, mystery, and biography. And since this is an enum, we can go back and add, delete, or change values at any time. Now that we have our genre, we can add it to the book object class. We can link it to the enum and make it cardinality many. Again, because we don't need to store any more metadata about these genres, this is a good use case for a multi-reference property. So now we've configured our data model so that a book can have many authors and many book genres, just as the task wanted. So let's check this task off and move on to the next one. A book should have a cover and only one. Now this means we need to add a way to upload images, which can then be linked to each book. So we need to add a new file object class. So let's make a new object class. We'll call it book cover. We can tick this box here to make it a file object class. You can see that file object classes have a lot more fields which are created by default, which holds information about the file which is uploaded. Now let's add a property called book, which will link a book cover to a book. Make it cardinality 1, make it required and unique. Let's add a cascade delete on this as well, so that we delete our book covers if the book is deleted. So now we have a file object class where a book cover can be uploaded and linked to the relevant book. This solves this task as well. All books and authors should be maintained through a third party using the GraphQL endpoints. So let's configure these properties on the book and author data sources. Now you can see that on each object class you have the option to enable GraphQL. And this opens up even more properties. So let's allow to read, create, update, and delete a book object from GraphQL. You can see that these objects have now disabled the opportunity to do strict object versioning, as there's now a third party which can update these objects while the app is in use. Let's make the same changes for the author object class. We'll enable GraphQL have the possibility to create, read, update, and delete an author from GraphQL. So now our data model is configured for GraphQL. Finally, we need to log the events of an order in some way. So for this, we can create a new object class called order log to be able to track the events and when they happen and what happened. Let's add a final object class called order log. Let's link an order class to an order. Cardinality 1 should be required. And again, we should make use of the cascade delete functionality. If an order is deleted, we should automatically delete all order log objects linked to this order. To be able to describe what happened in each order log, let's add a new property called message of type string. And this should also be required for each object. Now finally, to track which user is relevant in this case, let's turn on created by for this object class, which will automatically link the order log object to the user that is logged in at the time where the object is created.